So I think it's time to start now. Hello, everyone, and welcome to the drill string design session presented by Engineer Yusuf Salam. Engineer Yusuf has petroleum engineering degree from Cairo Engineering University in 1984. He has started his career as drilling engineer and drilling supervisor for GAPCO and then Petrobel until the mid-90s. He later joined Schlumberger Drilling and Measurement, where he went up through the ranks up to a drilling engineering manager, supporting multiple locations in the Middle and Far East and working with several operating companies. He joined British Petroleum Egypt's Gulf of South operations and drilled extended reach wells with highly depleted reservoirs. He then transitioned to the Mediterranean deepwater HVHT gas exploration as drilling engineering team leader. In 2021, he started working as drilling engineering instructor and trainer for Petroleum Engineering Department in the American University in Cairo, and also training and developing competency assessment of well engineers and drilling supervisors in the oil and gas companies in Egypt and Middle East. It's such a great profile. The pleasure is ours, Engineer Yusuf, for having you for tonight for today's session. So it's time to start our presentation. The mic is yours. Engineer Yusuf, I'm sorry, but you are muted. You can unmute yourself. We can't hear you.
Hello?
Yes, we can hear you now.
Can you hear me? Excellent.
Yes.
Thanks, Adil, for your introduction, and thank you all for coming to end this session. Let me share the
Okay, you can share now.
share screen. Can you see it now?
We
Can you
can't
see
see
that?
it. No.
Can. Just a second, I'll try again.
Okay, no problem. Yes, it's loading now.
Can you see
Yeah,
it?
we can see it now. Yeah. All right.
Okay, as I said, thanks, Adil, for introduction, and thank you all for coming to attend the drill string design session. We are going to talk about drill string, just focus on 3 points. The function of drill string in our well planning and well design, and then drill string design, how to design the PHA, and how to design the drill pipe. So we're trying to crunch 5 days course in only 1 hour. So before we start the design, the design is part of a big well delivery process. So when we start planning wells, we just get together the subsurface team and drilling team and then finance and safety team and just start going through a process to control the planning and the execution of the well. Yeah, this is common well delivery process for most of the oil companies, the big oil company, which is about 5 stages: appraise, select, define, and then execute and review. We start with the appraising and select, define. This is the 3 stage for planning. Before, in old days, we just say planning, but due to the criticality of the wells and the risk associated with well planning and the challenges we're facing, we just split the planning phase to 3 phases: appraise and select and define. And then at the end of each phase, we just get together as integrated team or the asset team, whatever you want to call it, and go through the activity and the milestone for each stage to make sure we're satisfying the process and nothing is missing. And then we'll go through the stage gate to the next one. And then we repeat it until we finalize the plan. And before we start executing on the operation, make sure any feedback coming from a defined stage or design stage is closed. And then finalize the drilling program and then start executing. Yeah. The execution is just follow up the operation while executing and then monitor the parameter and drilling parameter and the operation and intervene in the right time to control the risk and increase the performance. And then when we finish the well, we get together again and just review the plan, the drilling program and the operation, the lessons associated with the well. Yeah. So it's critical. The foundation of each well you will find is the bore pressure, frag gradient, and well trajectory. This is framework of each well. And then after that, you start designing the well casing and cementing and then fluid until you reach the beachy design and bed design and hydraulics. And then after that, you'll find the rig selection and sizing. And then when you finalize this, you go through the design and the risk it, see what is the risk associated with your design, and make sure it's acceptable according to risk assessment management or risk process. Whatever the risk management process you have to make sure the risk is acceptable according to your process. And if it's high risk, you have to put measure in place. You have to put measures, either prevention measure or mitigation to control the risk to an acceptable level. And then you calculate the cost and finalize your AFE. And then you're ready to start execution. So what I want to highlight here, just integrated project. So integrated work. So you have different interfaces from subsurface and drilling and then contractors. You have a lot of service companies associated with you. So the communication and the interfacing and how to manage the team while planning phase is critical. And then within this process, we start designing our well. Yeah. So while drill string design, you will get the service company and the contractor with you, and then you start going through the drill string design and beach design and bed design. So what's the function of main function of the drill string design? The first one, just make sure the structure will be intact. It will not fail while operation. And this we call it to maintain the stress, applied stress or maximum stress less than the yield stress of all the component or the weakest component of the drill string. The second one, transmit the axial and torsional load. You are rotating the string from the surface and you are applying weight on bed. So to make sure you are transmitting the weight on bed to the bed so you can drill, and at the same time you are transmitting the RPM, the speed, rotation speed or rotary speed from the surface to the bottom. If you have top drive, so you're transmitting the top drive speed to the bottom. If you have rotary table and Kili, you are transmitting the RPM to the bottom. Yeah. The third one is directional control and measurement. Part of the function of the drill string is direction control. You have in the bottom BHA, you will have some directional equipment. If it's your well is deviated or directional. So one of the objectives is to hit the target and to control the dogleg while drilling. Yeah. And at the same time, monitor this measurement while drilling. Yeah. to make sure you are implementing the plan. And if you are shifting from the plan, you need to control and take action, intervene and take action to follow up the plan. The third one or the fourth one is hydraulic, to optimize the hydraulics for the BHA. Any change in wellbore geometry, any change in drill string geometry, it will impact the hydraulics. So hydraulics and drill string designs work together. If you change the drill pipe, for example, to bigger drill pipe, you are going to reduce the pressure loss inside the drill pipe, which will give you more power to the bit. And then you put in your mind stuck pipe avoidance to make sure your BHA and string is designed to avoid stuck pipe. Still reduce the contact of the BHA with the formation. So you just put it in your mind after you design your well to satisfy the structure requirement. You say, what are you going to do with the BHA to minimize stuck pipe probability or to avoid stuck pipe if you can. We have a lot of equipment in the drill string. This is mainly, generally speaking, you have drill pipe on the surface and heavy weight, and then drill collar and jar. This is the basic, but you have a lot of other equipment, just like other tubular stabilizer. You have downhole motor, you have MEWD, you have LWD, you have pressure well drilling, and you have non-magnetic drill collar. So a lot of equipment, you put it in the drill string, which you have to consider well designed. Whatever you're going to do on the BHA and heavy weight and drill pipe, you're going to apply on these accessories to make sure to satisfy the design. One of the mechanical properties of the steel, which you apply in the drill string, is the famous stress-strain curve, which is the relationship between stress you put in the drill string and the strain. And if you see the green area, while designing and while operation, we stay in this green area to make sure your applied stresses on the drill string are within the yield strength, to not exceed the yield strength, which is the green area. The top one, if you continue on the line until you deform the string, you will go until to the maximum or to the ultimate strength, and then the string will deform it and it will fail, but will not reach there. This has a definition, you just need to know it. The area under the curve, we call it the ductility, and it's good to have some ductility, because when you deform the string, you don't want the string to fail immediately. This ductility gives you a chance the string will fail after some time. So in drilling, we call it will leak before break. So if we go to the ridge, you go to the yield point, or to the yield point will deform the pipe, and the pipe will leak small crack or something before you break. The break will be at the ultimate strength. Need to make sure load exceeding capacity, so stress exceeding the yield point. We don't want this to happen, so we stay under the minimum yield strength all the time. If the stress is less than the yield, so we are in the elastic deformation, which is the green curve. If the stress exceeds, the stress is the applied load acting on the drill pipe or on your string. If we exceed the yield, this will create plastic deformation and failure. Whatever the applied load you're applying, you apply tension or torque or burst or collapse, or sometimes you apply simultaneous load, tension with torque or tension with collapse. If you exceed, you will fail. But while drilling operation, we need to make sure we are not exceeding the limit. We have two failure mechanisms. When you design drill string, you put in your head two failure mechanisms. I want to design the drill string to avoid two failures. One, overload failure, and the second one is fatigue failure. The overload failure is the bulk strength must exceed the yield strength. If you fail on using the overload failure, you must exceed the minimum yield strength to fail. And it's acting the cross-section area of the tube, which we'll call it bulk stress, acting completely on the cross-section of the pipe. Fatigue failure is damage occur, we lose the yield strength away from the strength. If you can see the line here, fatigue failure acting as maybe 0.1%, 10% of the of the yield strength. But the overload, you have to exceed the overload threshold, which is the yield, to failure according to the overload, according to the overload failure. This one, fatigue failure, you don't have to exceed the minimum yield. Actually, it happens as very low figure, low number, which is critical, and act differently. Let's talk about this a little bit more detail here. You have the two threshold, one is fatigue and one is overload. The overload, you have to, bulk stress have to exceed the yield strength or the minimum yield strength, and the fatigue having 10% of the minimum yield strength. If you exceed the top one, the failure will occur. If you don't exceed it, failure not possible. And fatigue will be the same. If you exceed the limit or the threshold, failure will be possible. If you don't exceed, failure will not happen. And this is the operating stress range. Normally, we operate just a little bit under the overload or under the yield. The distance between ultimate and yield would be critical, so you don't have to go there because the string will fail. And the distance between the yield and the maximum operating range, it will be as a safety factor or alarm. Normally, we take into consideration as a design factor. You design your string to stay away from the yield there. Fatigue damage, the fatigue failure life, which is the critical. You can see the line of the fatigue life starting from new pipe at the left-hand side from A. And then you put the drill pipe in surface, maybe crack will be initiated in this area. And then will develop. After developing, you need to detect the crack using inspection company or inspection process before the crack propagates through the wall and fail. Normally, this area from A to B is about 90%. So it takes long time until crack develop, and then 10% and 10% to fail. So inspection of the pipe from B to C is very critical to detect the crack and take the pipe and put it out of surface and pick up new pipe. If the crack happens in drilling, we call it a string or shaft, small crack in the drill pipe or small hole in the drill pipe. We leave it and continue drilling, it will twist off or it's parted. Twist off, the pipe is twisted off, or it's parted. And you have some fishing hole, and then you have free string, and you go to fishing operation, and sometimes you cannot fish the pipe, you have to go on side track, put cement block, side track, and drill new hole. So you will lose the BHA, and then you lose the time for cement block, and then you lose the time to drill the hole again, which is big money. And if you have downhole tools inside the BHA, drill downhole motor, MWD, LWD, you'll find the cost. You have to pay the cost for the contractor, and the cost will be very high. We're talking about $2 million, $3 million if you have all the BHA and all the critical component from MWD, LWD, and Holia. What is the features of overload design? Bulk stress is higher than the yield strength at the weakest point. So you have a lot of component in the drill string. You need to make sure the bulk stress is, will not exceed the yield strength at the weakest point. If it happens, it means the bulk stress is more than the yield. But while designing to make sure it's less than the yield. A single catastrophic event, as soon as you exceed the limit, the string will be failed. You don't have, it will not be repeated many times. It's only one time. As soon as you exceed the limit, the body will fail. This is why it's easy to detect and easy to design. Driven by bulk strength in the component. And the bulk strength is really quantifiable and controlled because you have a number. And then if you exceed this number, the pipe will fail, which is different than fatigue. The fatigue is damage from cyclic stress that creates a crack. You are drilling and you're applying weight on bed. So the bead chain, the bottom or the drill collar under compression, and then you are rotating. So you are doing cycle stress. If you are drilling deviated well, or maybe low angle or high angle, you are changing from compression each side of the drill collar from compression to tension by rotating. So it creates cycle stress on the pipe and it fills with time. One event it will not cause failure, but together after many events or after many operation and after many application and after maybe after 1500 hours applied in the BHA, it can happen. So it will not happen from one event, it will happen from multiple events. So you have to track it and inspect it on a regular basis to control this failure. This is why we call the fatigue failure is difficult to detect here. It's a point stress. The overload stress is point stress, acting in one point, maybe acting in the tool joint, for example, or in the cross section between the tool joint and the drill pipe. So we call it concentrated area, high concentration area. And with time, it creates cracks, and the cracks start growing, and then growing, start creating a hole, and then hole start growing also and creating complete twist off or failure. Yeah. Stress in the tube. This is example. You will see it's acting the cross-section area and then acting the stress concentrator. Any crack, any slip area, any area while running pipe, any times you hit the drill pipe and you just have a dent and you have a crack, it will create with time and with operation a stress concentrator or stress concentration area. And this will be a weak point with time. It will the beginning of the crack. Yeah. The red area here, which is between the tool joint and the tube, and this also concentrated area, stress concentrated area. Why? Because you are changing the dimension of the tube to the dimension of tubing. Tubing, bigger ID, hence the tube, smaller ID. So you are changing the dimension. Anytime you change the section or you change dimension, geometrical dimension, it will find stress concentration area, which theoretically you have to put it into consideration here. Or when you move from drill collar to drill pipe, it is another stress concentrated area. The fatigue, as we said, it's a point stress and is calculated by just like pressure, load over area, but with a constant. We have a constant which this constant is more than 1, yeah, which is different. It's different to detect and also different than the bulk stress and overload design. Yeah. To summarize and see the difference, yeah. So you have two design mechanisms, one overload and one fatigue. Failure driven from this mechanism, overload about 15%, 1 in 5 every, or you can say 15-20%. The other one incident come 4 every 5. Every 5 failure you have 4 due to fatigue, or you can say 80%, 85%. So 15 versus 85. So the majority of failure in drill string comes from fatigue failure. Fatigue is driven by bulk stress in the first one, is driven in the second one by point stress. And point stress is critical to control, as we said, and will be critical also in casing when you go to casing design and see how the salt acting on the casing, it's acting the same way point stress. Threshold stress, which is value. This value, if you exceed the threshold stress with specific value above the yield, the overload will fail due to overload. If you exceed, the other one is 0.5 of the yield, but repeated many times. So a small stress acting on the pipe, but it's repeated 100 times until the pipe is failed. Easy stress determination. The first one is very easy. So you have number, and you try to stay under the number, and you have the gauges in the rig floor, and you make sure you are not exceeding the minimal stress based on the number you are monitoring. The second one is impossible for value. You just focus on, you monitor a lot of other things here to reduce it or to mitigate it. Accuracy of prediction, the first one is excellent, second one is very poor. Damage accumulate from well to well. It will not help you on the first one because you know the number, and if you exceed the number, you will fail. Maybe one will help you, yeah. If you fail due to fatigue, you can go back and see the history of the drill string and see why you are failed, and you can learn and you can learn from the history, and you come up with another strategy to reduce the fatigue on the next HA and the next drill string. Can an inspector evaluate critical dimension? For the first one is easy for the inspector to do it. The second one is impractical. It's difficult and impractical, yeah, because it takes a lot of time. Design method to use, yeah. This one is absolute. You have drill pipe grade S, for example, minimum yield stress 311,000 pounds. If you exceed this number, the pipe will fail. The other one, there is no number. You compare something with something, yeah. Last well, we had a problem from fatigue. So what we did, and then go through the steps and procedure we did it in the last well and try to improve it in the next one. So I will cover, for the time, I will cover the first one, which is the maximum stress is less than the yield divided by design factor or design. And then second one, we can take any question later at the end here. So you try to keep the maximum strength at any point in this string, in the drill string, less than the yield, derated by design factor. And I will call what is the design factor. Have a common design factor for each applied load. Select the component and configure assembly to retard the fatigue. You extend the fatigue life, and then you put it in, and you take it out of surface before it fails. Provide equipment that's resistant to hydrogen sulfide. It's a part of the design. If there is a H2S expectation. Drill string design nomenclature. This is some of the terms and nomenclature you need to know. So to design your BHA. And when you understand this number and this terms, you start using this in your design. Yeah, it will increase your learning process. Yeah. Tensile loading capacity. Start with pipe with tensile load capacity. What is calculated tensile bolt yield? How far you need to pull in the pipe until the pipe yield. And this is the starting point normally of the design. And then the design factor. What is the design factor? What you need to take into account in tension design. We call it design factor for tension. Because you have design factor for collapse, you have design factor for torque, you have design factor for BHA, excess BHA. So you have different design factors. So we call it design factor and put the symbol or the letter at the bottom, design factor for tension. Yeah. The allowable load, you take the tensile capacity divided by the design factor to give you the allowable load. And then the allowable load subtract the margin of overpull. So the margin of overpull, if you have a problem, what is the margin you want to have in the BHA before you reach allowable load? Say 100,000. So I subtract 100,000 from allowable load to give you the working load. I will go through this graphically later, but this is the term we're going to use when we talk about design. The reference, you need a reference, you get tensile capacity are given in the string DS1. This is the standard in the industry. And then you have API, RB7G, another standard from API. So if you want to see a reference or you read more, you want to read more about the string design, you can use one of them and you can use both. The DS1 is more detailed and it has about 4 volumes now. Yeah, one about how to select the pipe and bite, one about the design and operation, and another volume about inspection, and the last one about downhole equipment, which is supplied by the service company. This is a design factor for your design. It's a common changes from little bit from company to company, but this is a common for tension. We take 1.1, so 10% more, 10% less than the drill pipe capacity, tensile capacity. For collapse, 1.1 to 1.125. Purest for 1.5. Torsion, we don't take torsion because the makeup torque is less than the torsion pipe. So the pipe will not feel in torsion because we don't reach the makeup torque about 60% of the torsional strength. So you have already 40% less than the torsion. Yeah. Margin of overpull changes from 50 to 100,000. If you are critical, if you're well critical, you can go to 150,000 pounds as a spare. Yeah. If you need it, you can use it. If you don't need it, if you got stuck pipe and have to pull in the pipe, so you will use this margin of overpull. If you got tight hole and you have to work on the pipe, you will use the margin of overball. And then when you design your BHA, you have excess BHA weight, and the design factor for excess BHA is 1.15. You calculate the weight on bit, and then you add 15% more to make sure the neutral point inside the BHA. Buckling will not cover this because the time is limited, but when you drill deviated well, you don't run with the BHA in vertical well. In highly deviated well, the angle will be 70 or 80, and if you run the same BHA you have in the use for vertical well, it will create a very high torque, and you cannot drill it. So what we do here, we just remove most of the drill collar and just pick up first stand with direction drilling equipment, motor and RSS or RSS and MW, LWD, and then one stand heavyweight, and then put drill pipe. And drill pipe will be like this in the hole. So we'll be laying in the low side, and it will has buckling capability. When you put the drill pipe in vertical, has no capability for buckling. So if you slack off weight, it will buckle immediately. When you put in the low side support the pipe, and the pipe will have some buckling capacity. And it is function of the angle in the hole, and you have some charts to go and see the angle that the drill pipe specs, and then the angle, and then what is the capability of drill pipe. It's important in highly deviated well. You cannot actually drill with the vertical BHA in highly deviated well. BHA design. You start with the BHA design. You select BHA design on the right-hand side, enough weight so you can drill without buckling. If the weight of the drill collar is not enough, the neutral point will move the drill pipe, and the drill pipe will buckle. And with this, we need to avoid that. So you need to make sure you have sufficient drill collars or sufficient BHA to avoid getting the neutral point in the drill pipe. The neutral point we are talking here, it is the axial neutral point. So when I talk about neutral point, it is the axial neutral point when you move from tension to compression. Zero axial tension point, which is different from the pure buckling point, which you consider the pressure inside and pressure outside in your consideration. When you calculate the BHA, as we said before, maximum available weight divided by the maximum working load. The design factor will be 1.5. You make sure you have 15% more, just in case if you have a variation in the weight on bit, so the neutral point will not move all the way to the pipe, and the pipe could be failed. Select drill collar. General information about selecting the drill collar. You select it based on the size and weight and stiffness. The large drill collar, if you can, is the best, because it will give you weight on bit. You give you weight available to weight on bit. You need to consider the buoyancy and hole angle and design factor when you calculate the weight. If it's vertical, you just buoyancy and design factor. If it's deviated, you need to take the whole angle in consideration. The largest drill collar, high stiffness, which high stiffness resist buckling and give you smooth directional tendency, because the BHA is difficult to move laterally, so it will give you smooth hole. Cyclic movement is restricted because when you have a bigger drill collar, the space between the hole and the drill collar is smaller, and then there is no cyclic movement. So you are controlling the cycle, because if it's increased, it will affect the drill collar. You need to select the shortest to minimize handling time, to minimize the connection, minimize the drill collar in contact with the wall, because if you have many drill collars, the potential for sticking will be high. Differential sticking. And this is why in drilling, we're using a spiral drill collar. This is a spiral drill collar. The regular one has no grooves and will be slick. The spiral will have this groove, which reduce the contact area. When you have differential stack, the contact area is critical. When you reduce the contact area, you reduce the differential force acting on the drill collar. So if you have a potential for sticking problem, this is recommended to run with spiral direct collar. The other one we call it slick or regular. If you want to calculate the weight, this is the weight of direct collar. You calculate it based on the volume of the cylindrical volume, ODID, for 1 foot, and then multiply by the density of the steel. And then go through the units, you come up with this formula. If it's regular direct collar will be 2.67 times OD square minus ID square. ID and OD is in inches, and this constant. If it is spiral, it will be less, with about 4%, so this constant will be 2.56. So if you don't know the weight, you can calculate the weight from the dimension. Normally, you know the dimension of the pipe, OD and ID. So you can take the OD and ID and then multiply the relevant formula or the appropriate formula to calculate the weight. Yeah. This is how to prove, how to come up with the formula. Volume times density, and then you take the cross-section area times the steel density, and you adjust the unit and use the API unit, yeah, American units, to come up with 2.67 times D square minus D square. The first D is the OD of the direct collar, and the small one is the ID of the direct collar. Example, give you idea about how to calculate it. So you have the bead chain necessary, and necessary what is calculate the bead chain necessary for desired weight on bit, and give you the weight on bit, and give you the zoom factor, and given the mud weight, and then direct collar, OD and ID, and it's a regular connection, and you take to this, applying the formula straightforward to give you the weight, and then you calculate the buoyancy factor. For the people who can use a buoyancy factor is the steel density minus the mud weight divided by steel density. It will give you dimensionless factor, and then you take this one with the weight and calculate the BHA to give you 50,000. The length of BHA will be 50,000 pounds, which is the weight on bed, times the zoom factor. We need 15% more than 50, and then divided by the weight per foot for direct collar, which calculated here, yeah, and then buoyancy factor. This is the steps. How to calculate it? First one is the buoyancy factor, and then you apply the same formula we talked about now, and then for vertical, if it's deviated, you have another factor here, cosine angle. You need to consider it. And if you take this and then you put it on angle, say you put it in make a torque first, and then we'll talk about if we have angle involved. You need to make sure the makeup torque, and you take the makeup torque from this one and from API or B7G, and you ensure the makeup torque is lean. You don't exceed the makeup torque of the collar while drilling operation. If you exceed it, it will create problem, and maybe will create fatigue in the connection. Yeah. While drilling, the operating torque at any point should not exceed 80%. We are controlling from the surface, and the maximum torque acting will be on the surface, because the torque is generated from the bottom up the way well the surface, and then the maximum you see it on the top, and you are controlling this in your gauge 80% of the makeup torque. If the makeup torque is 10,000, we'll say 8,000 or 9,000. So you have a specific figure taken into consideration is the zoom factor to avoid exceeding the makeup torque while drilling them. This gives you makeup torque as a percentage from the torsion strength. And you see the maximum value will be about 60% for the last one here, about 50%. If it's less than 7 inch, more than 7 inch will be 50%. So the makeup torque actually is 50% or 60% from the torsional connection strength. So you are away, the makeup torque is away from the torsional strength of the direct collar. And this is a table, direct collar makeup torque from API, and you have the similar table from this one. If you need to make the makeup torque, you can go to the connection you're using, for example, 658 regular. What is the ID of the collar, and the makeup torque will be 53,000. Different pipe with different connection. So this one is based on the connection size, and then OD, and then ID, and then you take the makeup torque. Just to get familiar with the source of the data, either API or B7G or this one. When you design your BHA, you have 3 types of BHA. The first one we call it type A, drill collar, and you make sure and then heavyweight, and then drill pipe. And then when we design this type of BHA, you make sure the neutral point is in drill collar. And then you have the second one, you reduce drill collar, reduce the torque, for example, and then extend the heavyweight and make sure the neutral point inside the heavyweight. And then after that, you drill collar. Sometimes you can use 2 drill collar type, bigger drill collar in the bottom, and then smaller in the top, and then heavyweight, and then make sure the neutral point is in heavyweight. As the heavyweight is designed to run under compression, which is different than the drill pipe in the top. The most common one in vertical welds is very common. In the deviated weld, this one will be very common. Yeah, we reduce the drill collar as much as we can, maybe 1 stand, 1.5 stand, and then put heavyweight. If the angle is low, we put long string of heavyweight, and then drill pipe. If the angle is very high, we put 1 stand heavyweight and then drill pipe, because I will say if we have angle in the hole, the drill pipe will have some buckling capacity. You can put it under compression and drill, because the loose side is supporting the drill pipe. Let's understand what is the impact of angle on BHA design and calculation. If you have a vertical pipe, the weight will be weight cosine angle, and then the cosine of angle, if the angle is 0, the cosine will be 1, and then the weight will be 1 weight. Whatever the weight is, will be 1. So if you have 10K, you will have 10K. If you have 10,000, if you have 20K, will be have 20K. What if we have deviated angle and put 45 degree? What will happen? We'll say weight beside cosine angle, and now cosine angle, which is cosine 45, will be 0.71 times W. And W is the weight of the unit, the weight of the lens, either one joint or many joints. So you're actually using 70% of the weight available when you have 45 degree. If you have 75 degree, will be the same. You apply the same formula, and then you see what is the remaining weight you're going to use. Will be almost 1/4. So if you have 10K, we'll take 1/4 of the 10K. So with the angle, the weight available for drilling is reducing dramatically. So you have to understand this here. How the whole angle affects the BHA weight and side load. Increasing whole angle will decrease the component of drill string weight available to slide down hole, to drill, or to slide, and apply weight on bed. But at the same time, we'll do something else. Increasing whole angle will increase side load and decrease the string ability to carry compression and remain stable. As we said, if the angle is high, the positive outcome from this will be I can put some weight on drill pipe, normal drill pipe, without buckling, because this increase the angle, increase the string ability to carry compression, load, and stay and remain stable. So you have negative impact and you have also positive impact, and you have to see both, yeah, while design. What's the neutral point? The neutral point, under the neutral point, you have, when you put weight on bed, say 40,000, you will have the neutral point somewhere in heavy weight, and under this point, you have the BHA compression. Above this point, you have the BHA tension. And the position of the neutral point, the string, will vary with weight on bed. If you put more on bed, more weight on bed will move up. If you put less weight on bed, it will move down. If you change the angle and you put the same weight on bed, it will move higher also. And you will see it next slide. We have critical tool like the jar or some downhole tools. We need to make sure it's not at the neutral point. Because if you have the jar at neutral point, the jar will open and close and will be subject to fatigue failure. So either to put it in tension most of the time, or you put it under compression, but don't put it at the neutral point. If we have angle in the hole and use the same bottom bit. You are moving the neutral point to drill pipe, and you have to make sure the drill pipe will carry the compression. If it's not, you have to extend the heavy weight. You have to extend the weight to cover this point, and then apply compression on the heavy weight, because the heavy weight drill pipe is designed for compression. Or test the drill pipe and go to the graph and see if the drill pipe can carry the compression load without failure. Because as you said, drill pipe vertically is not designed to carry any load, but with angle, it will carry some load without buckling. Yeah. The higher angle, as we said before, will increase the stability of the drill string, allow normal drill pipe to carry higher mechanical compression load without failure. But the number will be in AY7G and will be available in DS1 standard. If you move this to the equation, you can go through it later, but you calculate drill collar by the bottom bit divided times the design factor, and then divided by the weight of drill collar per foot times factor cosine angle for rotary drilling. For slide drilling, you have to take the friction in consideration, because while sliding, you're sliding against the low side of the hole, and if you have irregularity in the hole, it will create some side force and some drag, and this you have to consider it while slide drilling, not while rotary. If you have drill collar, if you have drill collar and heavy weight, so you have to calculate the drill collar separately, and when you have the drill collar, you need to calculate the heavy weight, another formula, and this is the formula for calculating the heavy weight drill pipe. You subtract first for the drill collar from the limit, and then the remaining weight in bit, you calculate how many heavy weight drill pipe to reach the weight in bit. Yeah. So you'll have the weight in bit will be coming from both drill collar on the bottom and some heavy weight on the top. This is the definition of the weight in bit and the factor and drill collar and lens. I will leave it to you to read it later. Yeah. If you have a question, you can ask me later if you don't know it. Yeah. It's critical to understand the cosine and sine and then back this on high angle well or low angle well. In vertical, it's not considered, but in high angle well, it's critical to take it into consideration. Yeah. If you have type A BHA, as we said before, this is the formula to calculate it. You will calculate the length based on weight on bit, and then you take some excess here, 15% design factor for BHA, 15% weight more. So the neutral point, if the neutral point move up and down, it will not go there. And if it goes there, the heavy weight will not fail. But normally, the weight on bit coming in this case, in this type of BHA, the normal weight will be coming from the drill collar.
Excuse me, Engineer Yusuf. Someone is asking what does COF stand for?
COF? In this one here? Which slide?
Ahmadu, you can open your mic and start.
Which slide? Yeah. He
wrote it in the chat.
COF. Yes. That's a good question. Coefficient of friction. Yeah. While sliding drilling, you have sinal angle because this one will be normal. You calculate the normal force. When you calculate the normal force, you take the sinal angle coefficient of friction. So the friction is 0.3 times sinal angle and subtracted from cosine here, from the cosine angle here. So this term here is the friction acting on the BHA. And you only consider this when you talk about slide drilling. When you talk rotary drilling, you don't consider this because this is not impacting drilling. It's impacting sliding only. Coefficient of friction. Good question, Ahmed. And then we'll talk about this already. And then type B and type C, you have more heavy weight and less drill collar. You calculate this way. If we have to drill collar, you need to calculate the drill collar 1 and drill collar 2 weight and then subtract it from this term. Will give you the length of heavy weight. If you have one drill collar, so this one will be 0. Weight and length of drill collar 2. just like the first one, but we have two types of drill collar. Sometimes we run with bigger one on the bottom, 8-inch or 8.25, and then maybe 7 or maybe 6.5, and then you have 5-inch. So you are changing the dimension from 8 to 6.5 to 5-inch. So have a smooth transition between different pipe, different color and different pipe. Just exercise, you can go through it later, I do not here, but this is typical exercise, and you have the solution at the second slide. If you have the kick-off point and rate of build, ROB is rate of build, kick-off point, the first one is kick-off point. So you have vertical well, and you start kicking drilling direction well at 9,000. The build rate 3 degrees per 100 feet. Inclination will be 50 degrees. So you need to build 3 degrees per 100 until you reach 50 degrees. And then hole size 8.5 until you reach TD. Mud weight, drill collar used in the BHA, 6.25 times 2.5. 6.25 is the OD and 2.5 is the ID. And a spiral drill collar to avoid a differential pressure or differential sticking. And then heavy drill by 5 times 3. 5 is the OD and 3 is the ID. And the weight per foot 49.3. You're going to use 15 joint. This is the policy of the company in your calculation. And then design factor 1.1. Jar 8-inch drilling jar will be in tension when you design your BHA. Make sure this jar in tension, so you have enough drill collar weight below the jar to keep the jar in tension. You calculate the drill collar, and then you add 15%, and then you put the jar. So if the weight is moving up and down, it will not reach the jar. The last one is the coefficient of friction. It's 0.35, 0.25, 0.3. It depends on your experience and the mud weight using and your angle and the regularity on the hole. Yeah, different factor, and then you get from experience and you correct it later. Yeah. And then the question will be design the BHAs that will permit up to 20,000 pound weight on bit at TD while drilling in rotary and oriented. You start with oriented, so you need to use cosine COF, the coefficient of friction, and the sine angle in your calculation. And then when you do it in rotary, you just remove this term and you apply the same formula. And then what is the weight on bit will be available if drilling in rotary mode. Yeah. And when you calculate it, you'll find the weight on bit available to drill on rotary will be less than the oriented mode. Oriented mode, which is the slide drilling, you are not rotating. So you slide. When you slide, you have friction against your movement. Normally, the friction is against your movement. If you are moving down, the friction will be in another direction. So you need to consider it in your calculation while sliding. And this is a solution. I will not go through it, but give you an idea about if you're going to use the length of drill collar as a friction, as oriented or sliding, use the term here, cosine of friction times sine angle. Li is inclination or phi, whatever we call it. Yeah. This is the vertical angle you have in hole, which is 50 degrees. Yeah. And then you go through the application of the formula and calculate what is the length of drill collar. We don't have time to go through the calculation. Normally, in the normal training, we go stop and go through it and then calculate and then discuss it. After you calculate the drill collar, you divide it by stand. I need 830. So divide by stand or joint. The stand is 3 joint and the joint is 30 feet. You divide it 830 divided by 30. It will give you how many joints? Say 20, 29, 28. 28 will not be divided to 3. So we'll make it 29. When 29 divided by 3 will give you full stand to avoid stand less than 3 joint. And then take 29 drill collar and then you calculate in rotary mode what is the available weight in rotary mode using 29 stand times 30 feet every stand times 30, and then times the buoyancy factor, and then cosine angle, and then divided by design factor. It will give you the length available weight in bit. So you go through it, and if you have any question, you can send it to me, or you can send it to Adil, and he can send it to me. While drilling, as we said, we have tension and compression drill collar, especially in the divided well. So as I said, while rotating, in deviated well, one side is under tension, one side is compression, and then you continue rotating, you're going to change. The other side will be compression and tension and so on while drilling. And this acting is the connection of drill collar. And you have to make sure this will not fail with time. One of the features we're using, which is not 100% science, but it's taken from experience, is the bending stress ratio. And the connection of drill collar, we said the balance connection, which will not fail. And you can see the strength of the connection of the pin and the connection of the box will be balanced. Yeah, the same, it can carry the same load without failing. Yeah. It's 2.5 or the range. It's the range of the drill collar from 6 to 8 drill collar. So the range or the optimum range would give you the maximum life on the connection. It will be from 2.3 or 2 point something here until this point here, 2.7 or something here. The number is, when we start, they said 2.5 only, and then with experience, we found the range. The maximum life and the balance connection is not actually 1 point, it is a range. From 6 to 8, 2.5 until 2.75. So you need to maintain your connection with this range. If the pipe is more than 8, the suggested bending stress ratio will be a little bit higher. If it's less than 8, less than 6, will be different number, 1.8, 2.5. This is taken from experience, and then you maintain it and you apply it while designing, and at the same time you monitor the result while drilling. If you found when I use this still fail, you can change it slightly a little bit. You can go to 2.8, for example. Yeah. But if it's working fine with you, you don't need to change it because it's coming from thousands and thousands of application. Yeah. The other factor we need to consider while designing the BHA, we call it stiffness ratio. The stiffness ratio when you change it from drill collar to heavyweight, or from bigger drill collar to smaller drill collar. You need to control the change. You cannot change it from 10-inch OD to say 6-inch OD. The connection will be weak and it will fail. So control it with some number and say the stiffness ratio will tell Z lower and Z upper, and lower is the connection of drill collar, the lower connection, which is the box, and the top one will be the pin, and you calculate the Z factor, which is the section modulus of the connection of the box, of the lower drill collar, and then divide it by on the top one drill pipe, and then make sure it will be within 5.5. 5.5 for routine drilling operation, which will be a good number. Yeah. If you have a severe drilling operation, if you have high angle well, if you have extended reach well, if you have a deep water drilling application, you need to control it a little bit more. 3.5, which is controlling the change from bigger drill collar to smaller drill pipe. You want to make this one smooth. Yeah, change from 8-inch to 8-inch to say 7 or 6. It's better than to change from 8 to 5 and so on. Yeah, you see the change, you control it and make it more smaller. If the operation is severe, if the operation is routine and you don't have a problem while drilling and the failure rate is low, you can relax a little bit. And this is the connection in which you can see the connection. The one in connection we call it bending stress ratio, which is controlling the connection fatigue failure due to compression tension. The one between drill collar and drill pipe we call stiffness ratio, and control the change in OD to make sure it will be within 3.5 for severe and 5.5 for routine operation. And the same when we go from heavy weight to normal weight drill pipe, if there is a change in cross section area here, we control it also. Yeah, to make sure it will not fail while drilling operation. Yeah. So in drill collar, we call it bending stress ratio. On the shifting from pipe to pipe, bigger pipe to smaller pipe, we call it stiffness ratio, and controls the change in diameter. This is the BHA design. Well, now we're going to move to drill pipe design. Before we move to drill pipe design, you have the drill pipe specification you need to be familiar with, and this is available in EBI RB7G, and it's also available in DS. You have to understand the drill pipe and its fixed drill pipe and the connection of drill pipe and the strength of the tube, the strength of the tool joint, classification, marking, range, all the stuff related to the drill pipe before you design it. So for this one, you have start with 5-inch, for example. We call it nominal weight, nominal size, nominal weight 19.5. This pipe is very common in drilling operation. Yeah. So also all the rig will have this pipe available here. Maybe a little bigger and maybe have another one smaller, but this is the main and very common in all drilling operation. Grade, you have grade E and you have grade X and you have grade G and grade S. So in our example here, we grade S 135. Upset, the upset, the connection here, you have upset, you have some extension of the tool joint inside, some extension or upset, which is a little bit higher in strength. You can this one here, this is upset of tool joint. The OD is bigger than the tube, and inside the tool joint you find the ID is smaller than the tube, and this we call it upset. Either internal upset if it's from inside, or external upset from outside. And then you have the range. The range is controlling the length of the joint. What we use in drilling operation normally is about 30 feet long, which is range 2. And then connection, most of the connection of the drill pipe in C50, numbered connection 50 or 5-inch. So how we design it, and then classification. Classification is controlling the wear in the pipe. You pick up new pipe, put it in the well, and then subject to drilling operation and to when you drill deviated well, it will wear with the operation. When it wear, it will change dimension of the drill pipe, and you have to track the wear of the wall of the drill pipe. If it's new, the first one, and then call it premium, the second one, and then the third one will be class 2. So what we use in drilling operation is new and premium. If it's less than 20%, we don't use it in operation. But you have to track the wear in the drill pipe to make sure your specs is correct. And then you take the wear and the new dimension in your calculation while designing the pipe. So how to design it? You start from the top. You have to, we said either the pipe is either class 1 or premium. Class 1 is the new pipe. Premium is you have some wear. The tensile rating, you'll take it from DS1, or you'll take it from A by B7G. And then design factor. The design factor will be 1.1, either which is 9% from the tensile load. And you take another line, which is allowable, maximum allowable design for the pipe. This is your limit. Then you take the margin of all ball. If you get stuck and you have tight hole while drilling, what will be the margin? What will be the range to work with the pipe on? To use it to get the pipe free. And this will be 100K, will be 50K, you need to decide. The most common is 100,000 pound or 150,000 pound. Or using a by unit area. And then the remaining will be the maximum load, working load at surface, which is the maximum. This is your operating limit. If you got tight, you start using this area here. If you don't, normally we stay with this line here. And this one we call it working load at the surface. Yeah. And this is the range designed for drill pipe. And there is the V shape. Yeah. And our working load will be moved up and down based on your depth until the maximum line here. While drilling, got tight hole or got something or got stuck, I start moving this area. So when you're stuck, you cannot move the pipe. You start putting tension on the pipe, increase the tension up to this point. Try to get free, and this is your limit. Either before this, above this point, you will go to the critical area, and then the pipe can fail. If the pipe is new, you're taking safety factor also, even if it's new. If it's not new, you have to take the wear in your calculation. Calculate the new OD of the pipe, and then apply the formula and calculate what's the maximum tensile load, the maximum tensile or maximum rating on the pipe, taking into consideration the wear. If I take example, 5-inch 19.5 S135, you will find the new one is 560, and 560 is the new pipe, premium. This is the premium limit. Premium means, yeah, it's less than class 1. I take 20% wear. And then you subtract, take the safety factor will be at 510,000. And then subtract 100K, it will give you for 10,000, 410,000 pounds. So while drilling, the limit, my limit new limit will be for 10,000, 410,000. I will not exceed this number all the time. If I got tight, I have a range from 410 to 510. I can play in this area. If you put in graph, engineer like graph, tension versus depth, and then you go to the bottom and you take the margin of overball in the bottom here, say this is the depth, length of drill collar, and then the length of hip weight, and then the length of drill pipe 1, assuming we have 2 pipes, and length of drill pipe 2. In most drilling operation, you have either drill pipe 1 or drill pipe 2. So if you have deep wells, you'll have 1 and 2. If you have shallow well, you'll have only one type of drill pipe. But the majority will be, if you are drilling, say 15,000, 12 or 15,000 feet, will be 2 types of drill pipe, one in the top and one in the bottom. So to design it, we start from the bottom, take the margin of our ball. So you can take 100,000 here, and then start from this point, and then subtract the weight of drill collar and drill pipe, drill collar from this number, which will give you the new number here. This will be the tension at the top of the drill collar, and then heavy weight, calculate the heavy weight, and subtract it from this number, or add it, to add it to this number, will give you the limit here. This is the tension, or this is the weight at the top of the bead shape. And then you calculate drill pipe number 1. It will give you the new point here. This will be the tension at this point. And then up to the surface will give you the tension, operating tension at the top. Now you calculate this is the tension of drill pipe. You need to see the limit. You have to put the limit. How far the limit from the applied load, which I have here. For drill pipe 1, you take the rating of the drill pipe 1 from this one, or from RB7G, divided by the design factor, will give you a number here. Actually, this is the rating. You take the rating divided by this number, design factor, say 1.1, will give you the new number, which is allowable load, maximum allowable load. You apply the same on the top one. This is a rating of the drill pipe 2 divided by design factor for tension. It will give you a new number. The new number will be your limit, allowable maximum load on drill pipe. The difference between this red line and the blue line will be the load or the margin of overball available for you. But you have to consider when you have tight and you have a problem, you have to consider the minimum. In this point here, you have 0. You need the red line here and the blue line, it's in contact. So this is the maximum you can pull in this pipe, in the beach here, or in the drill string will be this point. But it's the maximum to pull on drill pipe 2. If it's drill pipe alone, you have some margin here. But you go through the beach here and see where is the minimum from the top to bottom. You will find the minimum this point. So I cannot exceed. I cannot pull anymore. My limit in this case will be this point. Or what I can do, I can change this pipe or can make it smaller and then use more drill pipe 2 in the design to give you more space between this area. Or you can remove this and use the higher strength pipe on the top. The design, this is overload design only. We have another design, slip crushing, the lateral force acting in the drill pipe while drilling. When you drill and you pick up one stand and then put slips around the drill pipe, you have lateral force acting in the drill pipe from side due to the load of the bead shape or the load of the drill string. Yeah, sometimes you need to consider this. If it's a deep well, you need to consider it. If you are drilling a deep water well, you need to consider it. If you are running casing under the beach, under the drill pipe, you need to consider it. If you are hanging, just like in liner, when we run liner on drill pipe, so you are hanging the drilling liner on the drill pipe, and the liner weight will be normal heavy. So when you run with it and put in the slips, drill pipe in the slips, you need to check this slip crushing to make sure the drill pipe is not crushed laterally, and then compare it with overload and take the minimum. This is the equation we use for graphical. So whatever we did graphically, this is the summary of the equation. You start with the tensile load times 0.91, or tensile load limit divided by 1.1. It will be the same. Actually, 0.91 is 1 divided by 1.1. Give you allowable, maximum allowable, and then the working load will be maximum allowable minus margin of overload. This summarizes what we said in the graphical representation. Nothing new. And the graphical even better, but I put it here just in case if you need it to design your BHA, you can use the formula for drill pipe 1. And if you have drill pipe 2, you have another formula for drill pipe 2. And if you have drill pipe 3, you have the formula of drill pipe 3. I'll go through it with you here. Just one example. For drill pipe 2, you have the working load of pipe 2 minus the working load of pipe 1. Pipe 2 is higher than pipe 1. And pipe 2 has strength, higher strength than pipe 1. So the strength of pipe 1 subtracted from strength of pipe 2 divided by weight per foot for drill pipe 2 divided by points factor. It will give you the length of drill pipe. If this length is enough to drill your well to D, fine. If not, you move to another drill pipe. Most of the time, drill pipe 2 is enough. Actually, we use either grade E and grade S, or grade G and grade S, which is enough to cover most of the well with drill. But if your well is too deep, say 6 kilometers or 7 kilometers, 20,000, 25,000 feet, so you may need another drill pipe. But your design is the same way. Yeah. If you need the drill pipe 3, say drill pipe 3 strength minus drill pipe strength 2 divided by the weight per foot for drill pipe 3 divided by points factor, it will give you the length required for your well from drill pipe 3. To summarize, we just talk about the BHA design and the drill pipe, and we said the maximum OD for drill collar, we need to choose the maximum OD we can handle and fish and drill with. Anything, any pipe, you need to run it to make sure you can fish it. So when you design your drill collar, you make sure you can go with overshot and catch it and retrieve it. So you have to keep the drill collar OD in a specific OD to be able to run with overshot and catch it from outside. So the space between the hole size and the drill collar is critical. Yeah. So when you design, this is something you need to check while designing the drill collar. Make sure you have sufficient BHA to keep the axial neutral bond in the BHA for most of the BHA, low angle well and vertical well. If it's deviated, we said we're going to reduce the bottom well assembly and run with heavy weight. And then you may run drill pipe, normal drill pipe in under compression, because in high angle, the drill pipe compression, the drill pipe can carry compression load. We call it buckling resistance. Can resist buckling. If you try to push it under compression, it will not buckle. It will not fail. It will not buckle first, and if it not buckle, it will not fail. But this we have to angle. The higher, the better. 50 degrees better than 40, and 40 degree angle, it has better than 30 degree. When you transition, you have transition. Dimensional transition or OD transition from drill collar to drill pipe, you have to check the stiffness ratio. And drill collar connection, to make sure it will not fail, you have to check the bending stress ratio. Drill pipe to withstand the load below the drill pipe. In a drill pipe you design, it has to carry the load underneath. So if you have drill pipe here and you have yours a BHA, make sure this connection carry all the load below this connection, below this point of interest underneath, yeah, with design factor. And then the one on the top will carry all the load hanging below. Either from while designing, you need to take into consideration stabilization, hydraulic optimization, and direction control. This is part of the objective of the drill string design. I'm running with the BHA to achieve the direction control. So what will be the bottom hole assembly? What will be the motor going to run? What's the vent housing you're going to run to achieve the build-up angle? And what is the MWD going to run? LWD, do I need LWD? Do I need restivity? gamma ray, you need density, and so on. Yeah, you will go through it, and then while designing, you apply the same load and same concept on the accessories on this equipment. Yeah, and also you need to consider the hydraulic optimization. Any change the dimension of the BHA, any change of the drill pipe, it will impact the hydraulics. So if your hydraulics is critical and you don't have enough hydraulics from the rig because the pump is limited, you have one option to change the drill pipe to reduce the pressure required from the pump. The bigger, the better. The bigger will reduce the friction inside the drill pipe. It will reduce the pressure required from the pump. And it will reduce the annular space between the drill pipe and the hole, which will improve the hole cleaning and improve the ACD. And this is the summary of our discussion. Any question?
Thank you, Engineer Yusuf, for this wonderful session. I really enjoyed it. But before we jump into the Q&A section, let's have a small break for 3 minutes just to fill the feedback form that I will send in the chat.
Okay, that's fine.
So we have 3 questions actually from First Willy. The first question is, what is the minimum safety factor? Is it the same with the design factor or not?
We just use design factor, we don't use safety factor because we don't reach to the failure point. So we are using design factor in the listing design. And before they use it, they call it safety factor, but no, we call it design factor. But even if you exceed this, the pipe will not fail, as we said at the beginning. It will reach to the maximum yield strength, but it will not fail. It will be deformed, but it will not fail immediately because you have a range from minimum yield strength up to the ultimate strength. But normally you call it design factor for tension, design factor for collapse, and we'll try not to reach it. Yeah. Well designed.
All right, thank you. For directional drilling, what equipment shall we use? RSS or motor or else?
Depend. If you have money, you can use RSS. RSS is much better from different perspective because you are doing directional work by rotating, and rotating is one of the factors for hole cleaning. It's very good. So if it is simple well and you're doing vertical well and you run with the motor for performance, you can run with the motor. If it's low angle, you can run with the motor. But generally speaking, the RSS will help you on because you are doing all the direction work by rotating. And rotating is a critical factor, especially when you have high angle. Yeah, if you can see the well, they split the well to 3 areas from angle point of view, vertical, and then build up section, and then extend reach or high angle, which start from 65 degree to up 90 degree. So if my design, I will recommend to run OSS in a high angle well to keep the bulbs rotating all the time. So I can keep the well clean. And if you keep the well clean, you will avoid a lot of problem associated with cutting accumulation in the angles.
Okay, perfect. Third question, does the drill string design correlate with LWD or MWD?
Whatever you're going to do in the string, you need to apply in LWD and MWD. So whatever design factor we're taking for BHA, it should be applied on MWD and LWD, the same design factor. Actually, when I design it in the software, I will put the limits and the specs of the drill of the MWD and LWD in the design, and whatever, and you'll find the heavy drill, the MWD and LWD limit applied load on the on this tool, and then the limit. The limits will be different from the limit of the color and the limit of the pipe. So you have some pipe here with different limit and pipe with different limit, just like drill pipe 1, drill 2. When you go down to MWD, to a different limit, applied load and different limit. And you make sure you have a margin of overball between the limit of the tool and the applied load in the tool. So I consider it part of the BHA, and then you plug all the number and specs and dimension of the software, and then you run software to come up with the maximum applied load on the string and the limit and the margin of overball available for you if you got tired or you've got problem.
Okay, thank you.
Welcome.
Amir is asking for the concept of jarring. He asked if you could repeat it.
The concept of jarring the jar, it's designed to work when you have problem. So you have mandrel and you have a housing, and then the mandrel is working inside the housing, just like the cinch. So it's free to move. The friction will be maybe 5,000 pounds or something. Yeah. So I don't want to be neutral. Neutral it will be with weight on bit, will open and close until it fails. So either put it in tension, it will stay open all the time because it's under tension, or I put it in compression and it's staying closed all the time. The mandrel is inside the housing and it's closed. But I need to avoid, I know this one, neutral point. Yeah, because this will open and close with weight on bit. Anytime I change the weight on bit, the jar will be open and closed. And this was time will create cyclic loading, and then the jar will fail. So we'll try to avoid it then. Either to put it in compression in highly deviated well and in deviated well, or you put it on tension as we do it in a vertical well and low angle well.
Okay, thank you. A question from Ahmadu. The design process is the same for directional drilling also?
Yeah, as we said, you just to consider the angle while designing. And you consider the torque. I did not cover the torque here, I cover only the tension. But while designing was cover the torque in deviated well. In vertical well, the normal force will be very small because there is no angle. When you have deviated well, you will find some of the BHAs acting normally on the low side. It will create friction, and the friction will create torque to overcome the friction. And then you can create the friction every joint until you go to the top, you'll find a big number over there because this is accumulated torque generated by the string. So while drilling or while designing the BHA, you need to consider this in your software. It will give you the number, apply operating torque. Take this operating torque, like the operating tension, and compare it with the makeup torque. We should have some space, some margin. Should be 80%. The operating torque should be 80% of the makeup torque. So you can call it over margin, it's not, or the space or the safety, or which is the difference between the applied torque and the limit. So you don't reach the limit while drilling. If you're getting closer to the limit, you have to do something. Either change the makeup torque or change the drill pipe to get a bigger high torque drill pipe, or maybe change the friction by changing the dope lubricant for the dope, drill pipe dope, and run and use dope with high friction. Normally, the dope we are using, the grease we are using for connection, it's one. So it's not affecting the makeup torque, is not affecting the torque. But if you need more torque, you can change this one here to 1.1 and request grease or doping, drill pipe doping with some friction to increase the friction of the drill pipe. So the pipe can withstand more friction and will give you more chance to drill deeper without changing the drill pipe. If you need more, you need to change the drill pipe to a higher torque drill pipe.
Okay, great. So a question from Emmanuel. He's asking, is the weight of drill collar in air considered when designing the drill collar?
When you design, you start calculating the weight in air first, and then you calculate it in mud. While drilling, when you calculate it in bed, as you can see, we divided by buoyancy factor. But first you calculate it in air and then divided by buoyancy factor, it will be weight on mud. And then you calculate from there. Yeah. You take the weight on bed, you take the buoyancy factor in consideration while calculation.
Okay, great. So the last question of today from Ahmado. How to be sure that our direction is respected during directional drilling? What do you mean by respected, Engineer Ahmado? Okay, to be sure that there is no any deviation from our design direction. So he's asking how to be sure that our direction, how to be sure that there is no any deviation from our design direction.
When you design your directional, we call it well path or well trajectory, and let's assume you are running vertical up to 1,000 feet and then start deviating, building 2 degree method or 3 degree per 100 feet until you reach 30 degree, and then you drill tangent. Tangent section means you are controlling 30 degree while drilling until you reach target. This is the plan. While execution or while operation, drilling operation, you have the tool. You have a tool to deviation tool, deviating tool, which is the motor or RCS, to give you the build rate or turn, whatever you want. And then you have MEW to monitor the result. If I am adjusting the tool, bent housing of the motor, for example, to drill directional and to build 2 degree per 100 feet. So every 200 feet, every 100 feet, I'm taking survey from MWD and see the result. I'm doing 2 degree per 100 feet, or I'm doing 3, or I'm doing 1.5. And according to the result, I start adjusting my sliding. So if I'm doing 2 degree, fine. If I'm sliding one joint and I'm taking, say, 2 degree build up rate as planned, fantastic, don't change anything. If I'm doing one joint sliding and I'm just getting 1.5 degree, so I need to increase the sliding slightly, another 10 feet or 15 feet, from 30 feet to maybe 45 to get 2 degree. And then take survey. And then the survey verification to what you did. If you getting 2 degree, fine, I don't have to change. Keep sliding the same interval to give you 2 degree. If something changed, if the formation changed, you can change accordingly to make sure you're. So you're doing by adjusting the tool to get what you want, and then measuring the result, and then adjusting while drilling until you reach 30 degree, and then you start drilling and adjusting to maintain the angle at 30. If the pitch is dropping, you need to slide little bit to maintain 30 degree, to build a little bit. If it's dropping slightly, say 0.5, 0.2 every 100 feet, so you need maybe small adjustment to build a little bit to maintain 30 degree until you reach TD.
Thank you, Engineer Yusuf. I think this is all for today. So thank you again for this wonderful session. It was really fruitful, and I've gained new information as adult. And also thank you for all the attendees for attending, and see you soon, inshallah, in our next sessions. Thank you, Engineer
very
Yusuf,
much.
again.
I really enjoyed talking to you. Thank you, and thank you for the attendance.
Thank you.
Okay, thank you. Bye-bye.